So the last problem that we're going to solve today by popular demand is example 3 on page 309. And if you have your book with you, you can look at the diagram and the question. It says there's a round hole of radius r that's drilled through the center of a half ball of radius a, with r, the radius r, being less than the radius a. Find the volume of the remaining solid. So basically you have a half circle or a half semicircle with radius a, and then you drill a hole of radius r, so this is r, and it wants you to find this region. So we all know this is the y-axis and that's the x-axis. So we know that x squared plus y squared equals a squared, because that's the formula for the circle. And it wants us to revolve this about the y-axis using two methods. First, we're going to use the washer method from the previous section 6.2, and then we're going to use the shell method from section 6.3. So let's go ahead and use the washer method. I remember we're revolving about the y-axis, and when using the washer method, if you revolve about the y-axis, you have to make the equation, the integral equation, in terms of y. So therefore y will be a function of x. So it goes like this. The formula for a washer is V equals pi times the limits of times the integral with the limits of integration from the first graph. This is because it's about the y-axis, so you integrate using the y, minus the second graph. dy. So in this case, you can easily see that the first graph we're going to use is going to be this one, the curve, and the second one is going to be this one. So basically we have to find the limits of integration, and that's, since we're integrating as dy being the differential element, this is going to be the limits of integration. So we have to find what this point is and what this point is. So this point, as we know, is a 0, and then this point is the highest point on the graph, which we're going to call square root of a squared minus r squared. So basically you should know why this is a squared minus r squared. It's because when you plug in r for the x on the x-axis, it gives you y squared equals a squared minus r squared. And when you take the square roots to find the value of y at r, it gives you y equals the square root of a squared minus r squared. So hence our formula is going to be rewritten as this: pi times the upper limit a squared minus r squared from 0 to the square root of a squared minus r squared, times squaring the first graph. We got to square the first graph, which the first graph is this circle up to this point right here. That is where we found this limit, this point. So we take the first graph as, it has to be in terms of y, so it's going to be x squared equals a squared minus y squared. To make this equation in terms of y, it has to be x squared equals a squared minus y squared, which turns out to be x equals square root of a squared minus y squared. So you plug that in here. square root of a squared minus y squared. You square it as f of y minus the next graph, which is just the line x equals r. You plug it in, and that's going to give you r squared. And you're integrating all this with the differential element dy. So I'll give you a second to absorb that. And then if you further disintegrate the equation, you get v equals pi times the integral from 0 to square root of a squared minus r squared. And you can square this. It'll give you a squared minus y squared minus r squared, all with respect to the y-axis. So you use dy to integrate. And you have to notice that a squared and r squared are just constants, because the radius of the semicircle is a, and the radius of the big circle is r. So those are constants of integration. So if you integrate this, it becomes pi from 0 to square root of a squared minus r squared times a squared minus r squared y minus y cubed divided by 3.
My battery's all over.
Divided by 3. 1 second. Sorry about that. When you integrate, you don't need the integral sign. So it's pi times that. From the limits square root of a squared minus r squared to 0. So basically what you do is plug this in to y, and then plug this also into y, and at the end of that, at the end of the manipulation, you come up with 2/3 pi times a squared minus r squared to the 3/2. And that's the volume by the washer method, revolving this omega by the y-axis. And we're expecting to get the same answer revolving this omega by the y-axis using the shell method. We're expecting to get this same answer. And this answer is basic. If you plug this in, here it's going to give you this value to the 3/2 minus 1/3 of this value to the 3/2. And that's why you get 2/3 of that value to the 3/2 times pi. So that's the volume.